Before we get started, does anybody have any specific questions, especially on the homework?
The automatic buffering and
Hmm?
the last part, the automatic buffering and explicit buffering. I can find any reference in the book, even though it asks us not very formula, but it's still.
Okay, so the buffering, the idea of kind of these ones that can grow or shrink, or if they're fixed size, whether or not the different calls, like how much they'll buffer. We talked about different sizes and things.
I remember from your lecture, I wrote it, but that is correct. It's the automatic and explicit.
Yeah.
That part is the one I was.
Let me see here. Automatic and explicit buffering. We didn't talk specifically about that term, but like basically think about like explicit buffering, saying how big a queue is, automatic, it being dynamic, kind of these limitless buffers types of ideas. Automatic is really referring to some of the things like the circular buffer we talked about, some of the automatic methods of dealing with the fact that we can't have infinite buffers, so we need a way of kind of, what are some strategies for doing that? What are some of the strategies we talked about for buffers that for essentially have no limit? There's two major strategies that we talked about in class. These are basically, what is it about something that will automatically buffer a request no matter what? What is the property in terms of like sending a message, for example? Because that's what this is talking about, communication between threads, inter-process communication. So what is one of the major things we saw with different styles of messaging? And it's also seen in synchronous and asynchronous communication. What do we see with these different styles of message passing when, if I know that it can always be buffered, what do I know about that call? Like if I'm sending a message and I know that sending that message can always be buffered, what can I say about that call to that send? What are the properties of these kind of different ways of sending and receiving messages that we talked about? I'm a process, I'm a producer, right? And I'm producing some sort of object that I'm going to let a consumer receive, right? So what are the issues that came up?
The main thing is if when it's produced, the receiver receives it right away or not. That's the main point coming from.
Well, that's not the only point. So one of the big points, yeah, that is a major point though. One of the major points is when I produce it, is there someone there to get it, okay? But there's all kinds of other variations on that, right? If the consumer's not there, what can we do?
Save it in buffer.
We can put it into a buffer, or what?
Or just stop later.
Try again later, right? But so trying again later implies what?
Cycle goes.
There's a cycle there, but what does that imply? Where does the object go? It might be thrown away, but if I'm going to try again later, I keep it, right? But what that implies is that the system, the messaging system, isn't holding it for me, right? But sometimes the message system can hold it for me, right, in a buffer. So right there, we already have a few different variations. One is we can try to send it, and something's already there, a receiver. So the receiver can immediately take it. No buffering goes on, right? I put it in, they take it out. Another option is I put it there, it goes into a buffer, and the person can get it later. Okay? So that's kind of from the view of, more from the view of the receiver or the operating system, right? Or the buffer. What about the view from the producer? Okay? There's different things that can happen depending on which of those methods I use. If the receiver's already there, what does that mean to me? I can give it to them, but what do I have to do after that? I don't have to do anything. If I give them the thing I've produced, I can move on. I can keep processing. I can keep, whether it's producing another object or going and doing something else. I can give it to them and move on. If they're not there and I can't buffer, what do I have to do? I either have to wait or have some mechanism to save it myself and maybe come back later. Okay? So, if the operating system, I know it's always going to have a buffer available, an automatic buffering technique that will take the message. From the receiver side, what does that mean every time I send a message? No. I don't have to look in there because I know that the operating system can take it. What is that called? When I'm those two different options of I'm there, I put the message there and they take it and then I move on, or I put it in a buffer and I can move on, or I wait for somebody that can come and take it. Blocking and non-blocking, right? Blocking is what? Wait until somebody picks it up. In other words, you wait. Blocking means waiting. Okay? So if I block, I wait. So in terms of blocking and not blocking, if there's automatic buffering that's always available, what does that say about my calls as a producer? I don't have to wait. It's non-blocking. Right? If there's some sort of automatic buffering mechanism. Okay? If there's some sort of fixed or explicit buffering mechanism, I may have to handle it myself. That's like a case of I go to put it into the, send it to the receiver, they're not there, so I keep it and I buffer it myself. There's not, the operating system doesn't provide that to me. Okay? Or it might be that there's a fixed buffer of some sort, right, that I can't put anything into, so I still have to block. Okay? I'll actually go back and see specifically what the author was referring to by automatic and explicit buffering, but that's the idea. The factors that come in there are this idea of, am I going to wait? Am I not going to wait? Sometimes, even if it's asynchronous, where I don't have to block, I still may have to do some sort of management of that object myself. In other words, just hold it and maybe come back. That idea of cycling through. Okay? I'll double check what they actually meant, but that's the idea. All of these are kind of, a lot of these are kind of the same, all in the same idea. The send by copy and send by reference. We didn't talk about that specifically, but it is talked about in the book. This is a phenomenon that we see also in other programming, like function calls and things. What are the two biggest trade-offs between sending by copy and sending by reference? Like, where do you see it? You see that in function calls as well, right? Like in C++ especially, C, right? When you send by copy in, for example, a C function call, what does that mean about the parameters that you put into a function? Let's say I have a function of some sort that says something like add in x in y. And then I say something like x equals x plus y. And return x. Okay. What do I know about, what kind of passing is this in C or in C++? No. Yeah, what other? Call by value, right? Okay. The reason it's called by value is this, because what if what's x? What's x? X is 1. Why is x 1? Right. So in other words, call by value means I call the function and give the values to x and y, but not x and y. Right? But if I do something like using, you can do it with like ampersand. There's a C++ has like a reference call, but you can also do it by something like that, right? And then we can do like the address of x and the address of y. Hey, now what is x? What is x now? Yes, 3. X is 3. Because now we've called by reference. In other words, we refer to the actual variable location, the variable itself, as opposed to the value that's in the variable. Okay? So, how could this come into play in messaging and communication between different processes? What are the variables in this case? The messages that we're passing, right? So these messages are basically data values, right? So if I want to send a message from one process to another, what do you think? How would call by reference or value come into play there? What is the big thing about call by value? What are the trade-offs there? Well, they both get the value. I mean, if I call by reference, the same value is there.
They just get the address and references.
Right? It just gets the reference. But why do that? What's the difference?
In this case, matches probably saved somewhere else with the address.
Well, yeah. I mean, if I give a mechanism, though, for getting to that address, like shared memory, some of the things we talked about. Shared memory, we can share a segment of memory and then let two processes look at the same address in memory. That's a reference, right? That's not by value necessarily, right? I could actually reference the same address, right? Whereas like with mailboxes or something like that, I would have to do by value because I can't let them both reference the same area. But what is the trade-off? Why? What's the big deal between the two? We've seen one phenomenon, right? Is that you can alter the value of a reference, and then the change shows up in both sides, which may or may not be good depending on what we're doing, right? But what is the biggest difference between by value and by reference? Okay. All our data is stored in memory in some way, right? Right? We're using memory to store these values, right? If I send you a message and I call it by value, what does that tell you about how we're using memory?
Memory is holding the whole bucket.
Copy of the message plus what?
Plus
the original, right? There's 2 copies of that message now. How did we get 2 copies? We copied it, right? Okay, so what does that say about message passing? Okay, if I'm doing message passing by value, right, that means I have to copy them, right? Copying takes time, right? Copying takes additional resources, right? We may be able to throw away the original copy once we're done sending it, but we're still going through this technique of copying from either, from one place to another. That's probably the mailbox, or copying it to kernel space, or some other mechanism. We're copying a message. Whereas call by reference is both of you look at the same spot. No additional work has to be done. You just both go there. Now you do have to worry about if values are changed, right? You need to realize that anybody looking at that particular reference will see the change. So we run into issues of synchronization and things like that. But it's the same idea, just in a different, it's the same idea of this, right? We need to be careful how we work with values that we pass to these different functions if they're called by reference or called by value. If they're called by value, we don't care what the function does to it. They can, change the variables and all that stuff, and we don't care. But there is overhead, right? Or if we want to change if we want to do it by reference where we don't have to copy it, then we have to be careful about how we use those variables afterwards. Okay? In message passing and things like that, this becomes more important when we start talking about bigger messages, right? If these messages are small, called by value, called by reference, the only difference really is can we change it and both processes see it, not the overhead. But when they start getting big messages, copying big pieces of memory takes additional overhead and things like that. So there's a trade-off. Okay? And then sometimes, as we saw with the different kind of ways of passing messages, sometimes we only have one choice, right? If we're message passing through mailboxes that are in the kernel and things like that, we have to copy by value. Okay? But I'll take a look at what everybody did for the automatic and explicit buffering, and I'll look through. I'll look at that from the book as well. Okay. Any other questions? Yes. So this first one, I'm going to be pretty lenient. So I probably won't take off for late submission for this one, but just this one, since we're all getting used to submitting it on WebCT. And I'm also going to look at it because it looks like when everybody submitted, a lot of the formatting kind of went away, so it's all kind of one big stream. I will look at the formatting to see what I can recommend to make sure that. Well, actually, somebody gave me an attachment. But no, I mean, what I'm talking about is you don't have to attach. You can just put it directly in there. It's just I think it's missing the formatting, the HTML formatting. So I'll look at that. Okay, so let me save a copy of this on my desktop and turn on my projector. We're going to be talking about scheduling, CPU scheduling today. Thursday, I'm probably going to bring in some info, at least some preliminary info on projects that are going to be done, at the end of the semester. I mainly want to bring it in on Thursday because this chapter has a lot of potential for you to find some things to look at for your projects. Okay, scheduling, and especially the low-level scheduling, like on a CPU, there's all kinds of different things you can look at there. It's a very kind of rich area of operating system theory and architecture theory and things like that. So CPU scheduling, it's very, very exact, very specific, and it's also usually the formula and the techniques that are used are relatively simple because they have to be done so often and they have to have such little overhead that you can't have very complex mechanisms there. Because if you do, you're going to spend most of your time scheduling and none of your time running actual programs. Okay, so CPU scheduling is kind of the area when we were talking before about multiple processes and how we schedule multiple processes, CPU scheduling is kind of at the level of the short-term scheduling, right? We saw some kind of references to some other types of scheduling, like long and medium term, and those can happen at a higher level, where the kind of general, like more coarse way of looking at processes of whether or not I should put a process into the ready queue and things like that. That's the more long-term and medium-term scheduling. Short-term scheduling is I have all the processes, they're ready to run, and how do I put them on the CPU so that they can actually start executing instructions. So this is the real low level of scheduling. Okay? So we're going to take a look at, today we're going to look at kind of the major scheduling algorithm, some basic scheduling approaches. On Thursday we'll look at some more specific examples with things like some of the approaches of different operating systems, of modern operating systems. Okay. So the basic concept with CPU scheduling, okay, maximize CPU utilization, okay, and we usually do that by manipulating how we utilize the CPU so that we can kind of take advantage of burst cycles of CPU and I/O. Okay. CPU and I/O. What are those? What is it about those two pieces? What types of things are I/O? Accessing the disk, right? Getting keyboard input, outputting to the display, the monitor, right? All of the network, getting network traffic, things like that. All of these are I/O. Okay. CPU is just CPU, just running instructions on the CPU. Okay. What do you think is the balance between these? How are these two related when it comes to? We're worried about CPU scheduling. Why are we mentioning I/O? Well, yeah, I will need the information from there. But what does this have to do with how we? I mean, what is this? What is it about input output that's important to us when we're scheduling the CPU? I mean, assume we have everything that we need to run at a given time. We have things to put on the CPU.
I/O time, it can come whenever.
Right. So whenever in a single like in a particular program, right? A particular program is going to have CPU and I/O, right? And we don't know when I/O will happen. Okay. So one thing is that we don't know when I/O will happen, so we can't really. We can't really necessarily foresee that it's going to happen. But what happens when it does happen? We interrupt and then we go handle the I/O. But what does that? How does that help us with CPU scheduling? Okay, let's go back to the idea that you brought up, that we'll probably need the data from that I/O to do some sort of processing. Okay, so I'm a process. I'm running instructions. And then I say I need some data from disk to do my next calculation. So what will I do? I'll interrupt, right? And I'll ask for disk information. Okay? So what am I going to do at that point? I ask for disk information. So do I get it?
Yeah,
It takes a while, right? Okay, so during that time, what am I probably doing in my process? I'm probably waiting for it. So what do? Run another process. So this idea of I'm going to be running a bunch of instructions, and then I'm going to ask for disk, let's say. So then I'm going to be sitting there waiting for disk, right? And it may be multiple blocks of disk, right? So I'll be waiting for a bunch of blocks of disk. Waiting, right? And then I'll get all my data. It'll interrupt, the system will call me back and say, hey, I got all the data you asked for from the disk. And then what will I probably do? Bunch of CPU, calculating, using these are those bursts. So there's a CPU burst of calculating, an I/O burst of interacting with input-output, CPU burst. So the idea is, if we have bursts of CPU and I/O, let's design a CPU scheduler that makes it so that we can kind of do CPU bursts while I/O bursts and other processes are happening. The idea is let's line up our CPU bursts so that the processor is always calculating and never just all sitting there waiting for I/O while the CPU just sits there doing nothing. Because every time the CPU sits there doing nothing is times that you could have been running programs, because chances are later on you'll have multiple programs that want to use the CPU. Okay, so if you can squeeze it into those times when everybody's waiting, you're getting better utilization of the CPU. Okay, so that's the goal of scheduling. Okay, the really hard part about this are a number of things. Is one, it's we don't necessarily know how to order these CPU bursts so that we can fit them in. Okay, typically scheduling is a NP hard problem. You can't schedule. There's no algorithm that you can do to definitely schedule. It's usually done through heuristics of some sort. Another thing is we can't foresee necessarily what kind of CPU utilization we'll have. Okay, because typically if we're running a program, a typical set of instructions or whatever, we can't necessarily determine how much CPU time we need from looking at a set of instructions unless we run the set of instructions. Can we do it by the number of instructions? No, why not? What are some of the issues that come up? Sure, so like we could call some other set of instructions. What else? What's one of the biggest ways that programs typically don't necessarily take a long time because they're long, right? Okay, if I tell you I have a 100 instruction program and I have a 10 instruction program, you don't know which would be longer, right? But you've probably written, like what you're writing, you've probably written some programs that take a while, right? Even though they're short. How do you make a really long-running program besides sleeping or just pausing and just a few lines of code? Recursion's one way, right? So if we recurse, in other words, have a function that we call the function, in which we call the function and dig deeper, and then eventually stop calling it, then unwind. That's big. What's a simpler way? Just loops, right? Are all the instructions in a set of instructions going to be executed? If I give you 100 instructions, will 100 instructions run? Not necessarily. What are some of the big ways? What's the main way that we don't execute instructions? If, then else is really one of the big kind of programming constructs that we use that is explicitly to make some code not run, right? If you have an if and else, half of it's not going to run, right? So it's hard to tell how much CPU we're going to use. Okay, so that's the hard part. Is we want to make it so we can use the CPU as much as we can. We want to order our use of these CPU bursts so that we can use as much as we can. But we don't know what the CPU bursts are. So that's the problem. It's saying schedule CPU bursts, but I'm not going to tell you how long the CPU bursts are, and it's an NPR problem. And you need to do it, millions and billions of times a second. So, no problem. Okay. So this idea of we have these alternating bursts, right? It would be great is if we had another program that had alternating sets of bursts, but shifted down a little. That would be ideal. CPU burst of another program here, I/O burst of another program here. CPU, we're never that lucky, but that would be the best thing, because now we're doing 100% CPU utilization. Our I/O is 100%. Great use of resources, right? Okay, but it typically isn't. We typically aren't that lucky. A histogram of CPU burst times. Okay, so what this is saying is these are milliseconds. Okay, and then these are the number of how often those bursts of that size come up. Okay, so what does this histogram tell us? There's a lot of short bursts and a whole lot of short bursts, right, compared to all the others, right? So we have a large amount of short bursts, okay, but we do have the potential to have very long bursts, right? They're just not as often, okay? So this brings up these kinds of patterns. These come from study of running programs and things like that. So what we need to do is we need to come up with some kind of algorithms that can schedule these bursts so that we get good utilization. But studies like this looks at actual programs and their CPU burst times. These help us tailor or choose algorithms that work best in real-world scenarios. Okay? Because you may come up with an algorithm that does very well worst-case scenarios of scheduling any length bursts. In other words, you give me any arbitrary set of bursts, I can schedule them in a way that is a fairly good worst-case scenario. Okay? What algorithm would be better, probably, than one that can schedule any set of jobs?
One that's good at scheduling the size of bursts and having them.
Right. So if we can schedule all of these, perfectly, and do very badly at these, longer running ones, chances are our overall performance, our theoretical performance would be maybe worse than this other algorithm, but when we're running on an actual system, we schedule better. Which do you think is more popular? Well, the one that does better, right? The one that does better on real systems that you're going to use, right? The other one might be more interesting for writing a research paper or something like that, but in real-world use, a real operating system will choose one that can schedule real traffic loads better. Okay? Because even though we might take a hit when these long jobs are running, these jobs that have very long bursts are running, or the long bursts in a particular program come up, in the grand scheme of things, it might be all right, unless we do really, really badly with these longer bursts. Okay? So, a CPU scheduler selects from among the processes in memory that are ready to execute and allocates the CPU to one of them. You remember the state diagram we saw of the different states that a process could be in? Okay, we can be, we could be starting, we could be waiting, or ready, right? We could go into running. Okay, we could be waiting for I/O or interrupted, waiting. Okay, or we could be done. Those different states that we go into. Okay, so the CPU scheduler's job is, I have a bunch of jobs that are in the ready queue. In other words, I could put them on the processor right now. I need to choose one to run next. Okay, how can I do that? CPU scheduling decisions may take place when a process switches from a running to a waiting state. Okay, switches from a running to ready state, switches from waiting to ready, and terminates. Okay, these two right here, 1 and 4, they say they're not preemptive. In other words, 1 and 4 kind of happen. The program kind of decides to enter the 1 and 4 states. Okay? Switching from a running to waiting state, I explicitly go to a point where I need to wait. Whether it's for I/O, I say I want to read disk. I'm kind of telling the system, hey, I'm waiting for I/O. In other words, I'm waiting, so don't schedule me. Right? But I've chosen to go into that state because I've decided to go get I/O. Okay? Terminates, right? I get to the end of my code, I'm kind of telling the system, I'm done, right? You don't need to schedule me because I need you to actually clean me up and get rid of me.
Why you should be there?
What?
The one is
Oh, well, we still need to get rid of it. I mean, we still need to, like, free its memory and stuff like that. So it still needs to be there, but we don't need to allocate CPU to it, except in the sense of reclaiming its resource. But we need to get the job out. We need a mechanism for getting the job out. So what we use is this kind of terminated, this done state, so that we can go in there and do something. Okay. These two, though, right? These are preemptive. In other words, the operating system makes the decision to schedule for steps 2 and 3. In other words, you're running, and you could actually run more, but I'm going to switch you from the running to the ready state. In other words, take you off the CPU and put you back in the ready queue. And I'll get back to you when scheduling permits, but I'm telling you to stop. Okay? Or, right, from waiting to ready, that one's a little different. That's not necessarily the operating system moving. Well, it is the operating system moving, but waiting to ready, you get into the waiting state, okay, in times like this where you do, for example, I/O. How do you get back from waiting for I/O? Okay, I go to the disk and I say, I need this block of data off the disk. Then what will happen? The disk will go run off and read data off the platters, and then what will happen? It'll finish reading the data, what will happen? But how do we do that? How do we get the program to get the data? We interrupt. Right? So when we get done reading off the disk, the I/O will kind of send an interrupt saying, hey, disk is done. So what will happen is the operating system will say, oh, I'm interrupted. I'm going to go to my interrupt code for this disk and see what I'm supposed to do. And what that will say is, I'm done. So that process that called me, that called for this I/O, is it still waiting? No, its data's ready, right? So we'll switch it back from waiting to ready. So in this case, it's preemptive in the sense that the operating system says, hey, stop. I need you to get off the running queue and go into the ready queue because I'm going to run something else. In this case, it's the disk saying, hey, I'm done. Whoever called me doesn't need to wait anymore. The data's ready. Okay? But these different styles, these two different areas, right, of preemptive and non-preemptive, depending on your operating system scheduler, your CPU scheduler, you may be able to do things in different. You may have all of the scenarios or some of the scenarios. So, for example, in systems like Windows before around like Windows 95, and in operating systems before, like Mac OS before OS 10, okay, and these types of operating systems, these were cooperative multitasking, and I've kind of mentioned this a little bit before. Cooperative multitasking, you kind of switch between processes by programs yielding the CPU. In other words, giving the CPU up so that other things can use it. Okay? What scenario do you think that falls into? Okay, I'm a program, I'm running along, but I get to a point where I don't really need the CPU that much, so I'm going to yield to the operating system. In other words, let it schedule something else. So what scenario is that? Number one, right? It's this kind of, I'm going to go into the waiting state myself. Okay? But I'm not being preempted, right? I'm not having an external force come in and say, hey, you need to get off the CPU. Okay? And then obviously if I terminate, if I get done running, I yield the CPU again. Okay? In more modern operating systems, you don't have to yield. You just run and run and run, and then you'll get preempted. Okay? The cooperative multitasking operating systems that can schedule based on kind of these first and last scenario, that's easy, right? You just go in there and just make a loop, right? And say, I'm going to schedule by whenever a program yields to me, I'll choose a program to run. Right? It's very simple. What's one of the big drawbacks? What if a program gets into an infinite loop? Will 1 or 4 ever occur? No, right? 1 or 4 will never occur. So what happens? No other program gets to run. So you have one bad program. Somebody forgot to put in, double equal sign instead of they put in a single equal sign in their while condition instead of a double equal sign, and next thing you know, you can't use your computer anymore. Okay? But it's easy. It's easy to schedule. It's easy to write the operating system, and it's easy to use as many resources as you want. Okay? Modern operating systems, preemptive. They have a combination. You still have the option of yielding when you're not using the operating system, or when you enter into states where you're going to be waiting for something like I/O, right? But then the operating system also has a say in how to schedule you, in that they're going to preempt you after times that the operating system determines. Yeah.
The one you said the data is ready, and the CPU knows that it's ready, and then the one was waiting for the data. Number 3 goes there, switch from waiting to ready. But why is not in CPU right away, or why we shouldn't be choosing first?
Oh, because we want to switch it back to ready so that we can just use the same mechanism of this. The scheduler goes and gets stuff from ready to run on the CPU. Because you can get into what if something else is already running? You can't go directly from waiting to running, because what happens to the thing that's on there? No, I mean, it goes back, and you mean into ready. See, you run into a problem with this. It's easy to kind of just skip a step and just say that, because you know what you do, right? If it's easy to say, okay, I'm process A, and I switch from running to waiting because I did some I/O. So I'm running, and I switch to waiting. Process B comes along. The CPU is free at this point, right? It was actually ready, and then it says, oh, CPU is free, I'll switch to running. And switches from waiting to ready because the disk is done and it interrupts. Okay, so should I go to running? I can't go to running because that's on running.
Because when the I/O is ready, it should interrupt process B on the CPU.
It did. It interrupted, and then it came back. The interrupt takes a short amount of time.
Yeah, then when it's interrupted and the operating system C that is interrupted and this I/O is ready, so you put the number B2 waiting queue.
So you're saying actually add in the interrupt here, right? And when this gets interrupted, right, we'll still switch to waiting, right? Or to ready. Back to ready. No, ready. Because it was running and we preempted it. Right? So this comes into running. Right? And then you're saying when this comes back, when this gets done, actually this goes to terminate. We should queue this one. I mean, we should run this one. So switch this to running. Right?
Yeah, because what is that? Probably that this guy is probably holding. That's what I think. I mean, if I get a interrupt on when B is running, the disk is ready. I think we should be, because it was actually A was there, so we should go back to where it was, and A should be load on the registers and with the disk now.
Okay. I mean, this is a valid scheduling technique. I mean, is when this gets done, we'll run this next.
Right.
Okay. But you're into a few problems here. One is the fact that what if B only ran for half a time slice? So you're saying don't give it the rest of its time slice Let's go to the other process. And you can do that.
It can save the like saving a state though.
Right.
If it's half done, you save the state.
Right, when it got interrupted.
This one is ready, so this gets.
Okay. What if this is constantly getting disk I/O? Are you saying never let B run its full time slice?
Piece by piece.
Well, I know, but what you're saying is B ends up getting half time slices through most of the job at that point. Is that fair to B? I mean, you say he was here first, but it's not his computer, right? The purpose of the scheduler is to make it so that everybody can use the computer. And while yours makes sense in the sense that you do save a context switch, right? If I'm coming back from a context switch, I might as well context switch back to whoever's going to use it, because I know it's going to be used. And it's a valid approach. But you can lead to situations of, it's called starvation. Starvation is when you don't let, there's never a chance for certain processes. Processes can get in a situation where they can't get part of the CPU. So your scheduling technique rewards I/O heavy processes, right? Because the more I/O you have, the more chance that your I/O is going to interrupt the CPU and steal the time slice away from somebody else, right? But you have the benefit of the fact that you know that CPU is probably going to run because the I/O that process was waiting for is available. Okay? But if something else was running, the CPU is already being used. So what are you worried about? You don't have a shortage of things to run on your CPU, right? So the more typical thing to do is when that interrupt gets back, you just switch this back to ready. Okay? And this guy gets to continue running after that terminates because you kind of do interrupts outside of the regular scheduling. You run it, put this guy back, keep running. The only thing different is this big guy became ready. So you don't have to worry about him not being able to get the data that he was waiting for because he'll just be scheduled in the next round of scheduling. So this guy will get done, but you ensure that all the processes kind of get their run. Okay? But that is, what you were talking about is a scheduling technique, right? It's a potential algorithm for scheduling.
And it does work on priority lists or something?
It depends. It depends on, we have all manner of choices. Okay? Okay. Dispatcher is just the module that does this, that does the actual switching of tasks. So the scheduler decides who's going to run next. The dispatcher is in charge of actually taking something off the CPU, saving its state, loading on the next one, and then running the next program. Okay? And the dispatch latency is the time it takes for the dispatcher to stop one process and start another running. In other words, the dispatch latency is how long it takes for a context switch. Okay? So these two different parts are very important. You need a scheduler to say what process gets to run next, and you need the dispatcher to stop the running process and put that next process on. Okay? So these are the two major portions of CPU scheduling. Okay? Let's take a quick break. And then we'll talk about the criteria and look at a few algorithms. Okay, so we'll take 10 minutes.
couldn't get WebCT to work this time, so I had to email it to you.
Oh, you emailed it to me?
But
Okay.
I didn't do B and C on the last question. That's what we were talking about.
Oh, what we were just talking about now? Okay,
so
that's fine.
I might go back and do them now.
Oh,
If
okay.
that's okay with you.
Oh, yeah, that's fine.
And I'll just try to resubmit it on, or submit on WebCT.
Okay.
So,
Yeah, that's fine. I mean, I'm not really that concerned about the individual pieces. I just want to see that you put
yeah, and it was
some of the other things.
just that, I didn't recognize the terms. I remember talking about buffering, but
I didn't really use the automatic and
Yeah.
explicit terms.
But now that you say that, I remember,
Yeah.
talking about them.
The different buffering
Yeah.
techniques. So yeah, I mean, that's my fault not looking at the terms that
Well-
he's explicitly used, but yeah, I mean it's really just the area of the buffering is
Right.
what I'm interested in as far as
I got you.
what comes out.
I composed it in Word and just I was gonna cut and paste,
No, there's also something wrong with how it's submitting. So
Oh, really?
I'm gonna check with, I don't know, it was like stripping out all the formatting, so that's all just one big stream. So I'll take a look at that. Do some test submitting from the sample student.
What's our first test, do you know?
I'm gonna have it, basically I'm gonna have it before the midterm grades are due, so people can look at before drop.
And that's like October 12th.
Yeah, something like that. I forgot where it is on the calendar, but what I try to do is have the test 2 classes before it, and then
So that's how we grade it.
I can grade it, give it back, and then
That's a good policy, I think.
yeah.
Some teachers do that as well.
Yeah, some you have to either haven't taken
Yeah.
the bulk of you haven't even taken the bulk of your grade yet, or you have to sit there and gauge whether
Yeah.
Did
You
I-
take the test, you
did
take
I
it off.
did I feel good about that
Yeah.
test? Did I feel good about that? Maybe not.
It's not fair.
See, that's the problem. If you're not doing well in the class, you're probably the worst judge of whether or not you did well on the test. I don't know, I read some article I ran across the internet about, I don't know, some psychologists did like all these tests on people, and their hypothesis was around like basically the, I don't know, how incompetency is like a tough racket, because the more competent you are, the better you are at gauging where you are as far as competence level. But if you're in competence, you always overestimate how competent you are in something. So, like they had all these where people took all these tests in different problem domains, like I don't know, like whether it was science or humor or whatever, and like the humor one was funny because people read jokes or something and gauged how funny they were, and to gauge I guess people who aren't funny are bad at gauging how funny something is, and they also think they're funnier than they are. It's along the same lines.
Yeah.
I'm always concerned when I'm real happy. Usually means I'm missing something.
So the project we're going to do, is that totally separate from the term paper that I would have to do? The research paper?
No, same.
Okay.
It's gonna be just all one thing. The main difference is just gonna be kind of content level of.
Right, I got you.
What I'm gonna recommend to most people is like I don't know, probably more like an experiment of looking at a phenomena or something, writing code or something that can see some of these things. But like, for example, the scheduling that we're seeing, that's usually a good candidate for, I'm going to write a bunch of things that have different bursts or whatever of CPU, and then I'm going to show like how these different schedulers, you can write a little simulator that shows
Yeah.
how different schedulers would fit them.
One of the assignments in architecture class, we asked us to do a kind of a presentation with a project. One of them was showing them the contents of the bus and the registers.
Oh, okay, and like each tick, like
Yeah, right,
you do a clock and then it will
right.
display. Yeah.
I thought it was interesting, but I had no idea. So,
Yeah, you usually, I mean,
sounds kind of similar.
yeah, it'd be a similar type thing. You just kind of show, here's the queue, here's like, here's the next job that comes and when it arrived.
Right.
You tick. And then the main thing is at the end you say, oh look, here's the average wait time, here's the average, turnaround time and stuff like that. So there's tons of stuff you could do with that. There's also other things like with cache and stuff like that. That's pretty, like cache, like we saw, like we briefly talked about. What should I do with pages that are already there, and I have a new page that needs to come up?
Right.
Like which one should I take off? You could say, oh well, least recently used does this, and this is how many times it page faults, and then you can do something like, oh, first come first serve. This is how many times it page faults, and look, one's better.
What's a page fault?
Page fault is when you go to cache, and it's what you need isn't there.
Oh, like a miss.
Yeah, a miss. Cache miss. Page fault is usually in terms of memory and disk. So, yeah, I usually call it, cache hits, cache miss up here, and then page faults down here. I can't get on the cat chat. Do you know who did I talk to about that being broken? I know. I'll have to plug in.
I didn't have any trouble with it.
So you just got on right now? It's the same as your web, like for the web stuff, right? Like webmail and all that.
Yeah.
Yeah, it's the same. It's basically your Novell account.
Oh, I guess it's the same.
Stop around. Okay. I'm going to try to get through. I'm going to try and get through at least most of the basic scheduling algorithms. I want to try and get through some of the different queuing techniques, but if we don't make it to that, that's all right. We'll just do that on Thursday. But all the examples of operating systems we'll do on Thursday. Your book is actually very good in this area, mainly because you can pack in a lot more data about these different scheduling scenarios. It's on page 150. It starts around 158 to look at the different algorithms. Okay, but like I said, I'm planning on bringing some info on your what you need to do for a project on Thursday, because areas like scheduling, CPU scheduling especially, are very rich for projects where you want to do some observation about how different schedulers behave. There's a lot of neat little kind of very more obvious things that you can see about how these different algorithms perform. So it's a good area to look for projects. Another good area to look for projects will be memory management as well, because simulators. Anything where you can create some very straightforward simulators or some sort of thing where you can run through iterations of a relatively simple algorithm at each step, but as you run it over and over and over and over again, it becomes more complicated. And that's really good for simulators because it's real easy to write a simple algorithm for the one step and then just let it run a bunch of times and use computers for what they're built for, which is running something a bunch of times. Okay? So these are some interesting areas. But the first thing that you need, especially when you're working with algorithms or with new techniques like scheduling, the first thing you want to do in any experiment is have metrics for measuring the performance of that experiment. Okay? So these are some of the typical metrics that we use to measure scheduling performance. Okay? So we have CPU utilization. Okay? Keep the CPU as busy as possible. So have the CPU running at all times, running active jobs. Okay? Throughput, number of processes that complete execution time per time unit. In other words, within a given amount of time, how many jobs have we completed? Okay? Turnaround time, amount of time to execute a particular process. That's on an individual process level. Turnaround time, each process has its own turnaround time. How long did it take from when I submitted the job to when I get the results of the end of that job back? Okay? Waiting time, amount of time a process has been waiting in the ready queue. In other words, not when I end, but when I start running on the CPU. The amount of time from when I was submitted to when I start running on the CPU, which is different from turnaround time, and that turnaround time is from the time I submitted till I get the job done. Those are very different. Okay? And then response time is the amount of time it takes from a request was submitted until the first response is produced, not the output. So this is more like the jobs can be smaller chunks of that job. How long it takes for the smaller chunks of that job to get done. In other words, start to finish may take 10 time units, but start to middle might only take 5. So a good response time would get that middle point done quickly, as opposed to the whole thing. This is important in things like our time sharing environments where you have multiple users using a system. Those users are running interactive jobs, right? And so you're not really as concerned with when the complete job finishes. You're really concerned with how often the job is serviced. Does that make sense? Because the more often the job is serviced, the more you get response feedback from like typing input and seeing stuff put on your screen. The faster that happens, the more often that happens, and the more timely that is, the better the system looks to you. In other words, your interactive experience is better. Okay? That's very different from these others. And you'll see that all of these are kind of in conflict with each other in a lot of ways. And the other thing is that you want to minimize and maximize different factors. So we have max CPU, right? We have max throughput, but minimize turnaround time, minimize waiting time, and minimize response time. Okay? And these are in conflict. One of the interesting conflicts between CPU utilization and throughput. Are those necessarily, if I maximize CPU utilization, am I necessarily maximizing throughput? No. It seems that way. It seems that way if you just say, I have 6 jobs, and I could maximize CPU utilization and maximize throughput by just lining all 6 up and running them through. That would maximize CPU and maximize, well, depending if they have I/O. But the idea is this. The trick with maximizing throughput and maximizing CPU utilization, you can actually have times of high CPU utilization but low throughput. Okay? The main time that happens is if, for example, you're context switching between a bunch of processes that are utilizing the CPU, but let's say your context switching is inefficient, right? And you're context switching too much. Is your CPU utilization still high? Why? Because the switches, even though they're not doing useful work, they're still using the CPU, right? But is our throughput high? Not necessarily, because if we're spending all of our time context switching, we're not finishing jobs, right? Context switching doesn't kind of count as a job, right? That's overhead. So in other words, high overhead or inefficient use of the CPU can still lead to high CPU utilization, but low throughput. Okay? But then CPU utilization also comes into play, like kind of in contrast with throughput, in that maximizing CPU utilization, I mean, typically will follow, you'll typically be utilizing a lot of CPU if you have high throughput, but it's not necessarily the case. I can't think of any examples offhand, but maximizing CPU utilization is really targeting more towards this idea of sometimes jobs aren't using the CPU, like they're doing I/O and things, so the CPU sits idle. So max CPU utilization is really looking at those idle times of CPU, and you want to use them as much as possible. Like, for example, just lining up those jobs in a row, that might be a fairly high throughput, but there might be times where the CPU is sitting idle, and you might be able to do better, okay, by like alternating and things like that, like what we saw where we alternate I/O and CPU. Okay, but usually these two are usually tightly related, though. Okay, turnaround time, waiting time, and response time. Okay, we've seen some examples already of this, how those kind of play off each other. Response time was that idea of we cut a block up into pieces and then just switch the little slices so that we are constantly servicing both jobs. Okay? But the problem is that the context switching takes up more time and whatnot. Waiting time and turnaround time. We saw that if we reorder some jobs, we might get them running on the CPU quicker. Like if we have a big job and some little jobs, if we put the little jobs first, right? So we see different things there. Turnaround time is, a lot of times we can't do a lot with that. Okay? We can do a lot with that if we minimize the overhead, like lining up jobs in sequence and not context switching between them. That's usually the only way we can usually get better turnaround time is by not exhibiting too much overhead, usually. Because really there's nothing we can do about how long, the fact that however long those jobs take, they have to sit on the CPU for that long at least. Okay? So let's look at some approaches. First come, first serve. Almost always a possibility in anything we do, right? One of the most straightforward things to do, especially with things like scheduling, is when they come up, you service the job, and then when it's done, you get the next job, right? Very straightforward. Everybody stand in line. Next person in line gets to use the CPU. Okay? So, they arrive in this order. This is their... What do you think they mean by burst time? Why would they term that as burst time? That's the CPU burst time. In other words, that's how long you can constantly use the CPU for. That's not how long the whole job might take, but how long you need the CPU for. The burst of CPU you need. So, 2433, P1 happened to arrive first. Service that for 24 time units, 3 time units for the next one, 3 time units for the next one, and we're done at 30. So the overall time was 30, right? There's not a lot we can do about that, right? That's the minimum amount of time that we can service this queue with, right? If it needs 24 time units, the other one needs 3, the other one needs 3. We have to at least use 30 time units. But the wait time for each of these jobs, the average wait time is 17. Okay? This can be changed pretty easily by moving jobs around. Okay? So we can look at the next type this is still first come, first serve, but let's say they arrived in a different order. Okay? So it's the same jobs, but in this case they arrive P1, then 2, then 3. Here they're arriving P2, P3, then P1. Okay? Notice what the average wait time is now. Right? It's 3 as opposed to 17. Right? So we've drastically altered the average wait time just by them happening to arrive in a different order. Okay? So can we explicitly have our scheduler do this? In other words, take the short jobs and make them run first instead of the long jobs. First come, first serve, we can't, right? Because first serve, what's the algorithm? Right, next line, service. Next in line, service. How do we alter what happens? Well, they have to come into the line differently, right? So we're kind of at the mercy of when the jobs arrive, okay? So you can go into more complex scheduling algorithms, like shortest job first, okay? So what you do is these different job lengths, you arrange them so that the shortest jobs are run before the longer jobs. So in other words, you attempt to achieve this ordering no matter how they've arrived. Okay? So they might arrive in the order 1, 2, 3, but then you look at all of them, you say, what's the shortest job? Well, the 3s are the shortest job. So I'll rearrange them into 2, 3, and then run 1 last. Why do we do that? Well, we've seen that we can at least improve one of the metrics, which is wait time. That's a big problem, right? I told you at the beginning that there were 2 major problems to scheduling, right? One is the fact that we need to be able to order these things in a way that maximizes some metric or whatever, which is hard in and of itself, okay? The other difficult problem, which is even worse, is the fact that how do we know how long a job will take? Separate problem, though. So what we're looking at is the first part, which is just how do I order jobs given their burst times. So we don't. How do I measure? How do I know how long they're going to take? I don't. Yeah.
Are there any systems or CPUs that say that there's a fixed burst length and that's all you get?
Yes. So that would be a round robin type of algorithm. Okay. Now, but looking at just at the simple one, like shortest job first. Okay. And also the other thing is we might use a lot of these techniques at other levels too. Like even though some of these might not be good for CPU scheduling, in fact, we usually use other methods for CPU scheduling like round robin and things like that. These might be good for long-term or medium-term scheduling. Okay, but let's just take a look at this. Shortest job first. You take the shortest ones, you put them first. One thing that's interesting about this is that shortest job first is optimal for waiting time. Okay, optimal meaning that if you arrange your jobs in the shortest job time first, you will get the optimal, in other words, the minimum average wait time for a set of jobs. Okay, which if you can know things about finding the optimal of something in these hard problems like scheduling, that's pretty good because you know that's what you have to approach if you have a new type of scheduling algorithm is you know what optimal is, it's shortest job first. Okay? But that's just for one metric, and that metric is average wait time. Okay? So, there are 2 variations, non-preemptive and preemptive. Non-preemptive, you get a batch of jobs, you schedule them, and then you let them run through in that schedule. But if a job is running on the CPU, it has to run to completion before you schedule the next thing. Okay? Preemptive means that when new jobs arrive, you actually can interrupt the currently running job and reorder your queue exactly at the point when the new job arrives. So what that means is a long-running job that's on the CPU might get preempted and stopped and another job run in its place if a shorter job arrives. Okay? That's known as shortest remaining time first, because each job, when a new job arrives, is stopped, and then the rest of that time is considered its job length. So let's look at how that affects the schedule. This is non-preemptive. Okay? So, burst time 7, right? The first job arrives. So what do? It arrived at time 0. We start running it. Okay? Job 2 arrives, P2 arrives at time unit 2. So that's 1, 2 right here, right? Can we run it? No, because this is non-preemptive and P1's still running. Okay? P3 arrives at time unit 4. That is here. Let me get my pen. Oh, this is not PowerPoint. Okay. This is P2. P3 arrives at time unit 4. P4 arrives at time unit 5, right? So at this point, we have 2, 3, and 4. Okay? So how do we order 2, 3, and 4? 3 goes first, and then 2, and then 4. Okay? Because given equal time, it usually is just first come, first serve after that, if you have 2 of the same time length. Okay? So we've reordered these as 3, 2, then 4. So by the time P1 is done, right, at time unit 7, we run 3, then 2, then 4. Okay? If something arrived here, we may or may not put it before 4, depending on how long its birth time is. Average wait time is 4, which is pretty good. But preemptive, shortest job first, same set of jobs, and that's what's interesting, is the same set of jobs, same arrival times. Okay? But what you do here is that at time 0 you have P1. When P2 arrives, right? Remember, this is also called shortest remaining time first, right? So at time unit 2, P2 arrives. Well, P1 has gone through 2 time units, so that's 5 time units left, right? So the remaining time of process 1 is 5 time units. P2 arrives, it's only 4 time units. So what do? We get rid of P1 off the processor for now. We put it back in the queue, and now we run P2. Okay? What's interesting here is that when it gets done, right, with its when it gets to time unit 4, it still has 2 more time units left, right? Because it started at time unit 2, it ran 2, and now it's time unit 4. It has 2 left. But P3, the tiny, tiny little 1 time unit job, arrives. It actually preempts 2 at this point and gets to time unit 5. Well, now what's left? We have the rest of P1, which was 5 time units, and we have the rest of P2, which is 2 time units. Well, P2 is the next candidate. 1, 2, right? But, oh, actually, sorry, it's even more complex than that. We actually, at the end of P3, P4 actually arrived, okay? But it's 4 time units, okay? So at time unit 5, our queue looks like this. We have, what's in our queue at the end of time unit 5? P4 arrived, we know that's there, right? P4, which is 4 time units. What else is in there? The rest of P2, but how much of P2 is left? 2 time units. So we have P2, 2 time units. And then what else? We have the rest of P1, which is how many? 5. So we have P1, 5, 1 time unit. So or 5 time units. Sorry. Right? That's what's left at time unit 5. And now we have to schedule something. Best candidate? P2. It has the shortest runtime left, so we run it. Time unit 7. This is done, right? No more new jobs have arrived. So next candidate? P4. We run the rest of P4. It gets done. Final candidate P5.
So, if, say at the end of
you'll probably continue running the one. Yeah. Mainly because if you fall back to first come, first serve, if you're running, you're obviously there before it. So, okay. And in this, notice that the average wait time is now 3. Before it was 4. So with the same mix of jobs, we got a lower average wait time. But what did we notice about this algorithm? It's a little more complicated. I had to get up, I had to write stuff on the board and keep track of, right? If I'm doing that, obviously the computer's probably doing that as well, right? This was straightforward, right? You have a queue and you just sort them. Okay? We never run into this problem of what do I do while this job's running if a shorter job arrives and things like that, because you have to run something to completion. But we get some better performance. At least by the metric average wait time. Oh, yeah, that's another key element here is the fact that we actually, here we didn't have any context switches. Right? Because they're getting done. Technically there is a context switch because these are burst times. So if we had burst times, we would context switch out and then maybe be able to run some more. But these burst times, the big point is that there aren't as many switches, mainly because we only switch at the end of a process's burst. So we're going to have number of jobs minus 1 switches all the time in non-preemptive, right? Here we've seen that we can add a lot more than that, just depending on when jobs arrive, how long they are, and things like that. Okay? So these types of techniques are good for kind of more medium, long-term types of things, because we do run into problems with these short jobs. Let's see if they make reference to that in your book for you. Actually, they reference it in a different context, but we can run into situations of starvation for processes. Okay? What starvation means is that, notice what happened to P1. Right? P1 was the first process to get to the CPU. Okay? But it ends up being the last one to be serviced. And in fact, it could actually be serviced a lot later if more short burst jobs arrive. If we get a constant stream of anything below 5 time units, right? They all get priority over P1. Okay? So in other words, what we can do is we can starve P1 from the processor. Okay? And obviously, what did we see about with the histogram of burst times? There's tons of short jobs, right? All very, very short, and then very few of these long ones. These long jobs can really, they can really get the short end when it comes to getting the CPU, because you might be able to run some of the job, but if you preempt and then start running something else, other things are going to keep taking that CPU and always be prioritized higher. Okay? What's that?
How do you determine the burst time of a particular process?
Right, so that question came up earlier, is how do we know what the burst time is? We don't. Okay? So what can we do? So this is the second half of the problem of CPU scheduling. Okay? We're going to see some more scheduling algorithms, but here we stop and decide, okay, if I'm scheduling based on burst time, that begs the question, how do I determine burst times? Well, we don't know the burst times necessarily, okay? But there are techniques. So what they go over in your book is one technique of using kind of a mix between your current burst time, because remember, these burst times aren't necessarily how long the whole job takes, right? They're bursts of CPU utilization in the same job, okay? So what they're doing here is a mix between historical burst times and your current burst time, okay? And what they do is they come up with a nifty little formula where they try to determine the next, that's actually should be a plus right there. That should be a plus, not an equal. Okay, they're trying to find the tau of the next time step. In other words, they're trying to predict the future times the future burst time by looking at the actual length of a current burst combined with the previous predicted value for burst. Okay? What this ends up doing is this becomes kind of a running history of your burst times. Okay? And this is your current burst time. So what it does is, I'm going to look at kind of, let's say, just trust me that this is the history of your burst times. In other words, all like kind of a number representing your previous bursts. Okay? And this is your current burst time. Okay? So what I'm trying to do is, what do I think your next burst time is going to be? No, it's this. Right? It's this formula is what I'm going to predict it to be. But here's how. So the question that it's asking is, what's the next burst time? Well, what I'm going to do is I'm going to take some portion of this historical value and some portion of the current value. And I'm going to make that be my prediction for the next value. So what we do is we put this weight in here, and then 1 minus the weight for a total combined weight of 1, right? So what we're going to do is take some of the historical burst and the current burst and make that as a judgment of what the next burst will be. So what do you think happens based on when I change this weight, this alpha? Okay, what if alpha is big? Which of these factors is more important? Right, so the current CPU burst. If alpha is low, basically the historical CPU bursts are more important. Okay? So what we're saying is, if alpha is high, right, then what we're saying is the current CPU burst time is the most important factor. Okay? Chances are your next burst time is going to be very similar to the current burst time. Okay? If we make alpha very low, this becomes high, right? And if that's high, what we're saying is your previous CPU burst times are more important than the current burst time. In other words, the current burst time is a fluke. In other words, the current burst time is some anomaly, whereas the historical burst time is probably more of a gauge of how you run from one time step to the next. Okay? See, because this is the history, okay, because it includes the actual burst time of the previous time step. Right? Because this tau right here is calculated from Tn minus 1 and tau n minus 1. Right? And that one is done from n minus 2, n minus 2. Okay? They have a good discussion of it in your book on page 161. Let me see if they write that up here. Yeah, here. See, if you expand tau, you'll see that it's a combination of the t's from the previous time step. So that's how it ends up rolling up these historical values. Are there better ways to track the historical values? Yes. There's more complex ways, but this is a good way because it's simple. And if your CPU's doing this, right, and you're doing this millions and billions of times a second, you need something simple. So this is a very simple, straightforward way of keeping track of all our burst times in the past, our current burst time, and then a weighting mechanism so that we can kind of emphasize either end. Different jobs might have different weights. Who knows? Right, a different alpha. Okay? So this is a very simple, very kind of clever way of taking into account CPU burst times so that we can use those as predictors of future burst times so that we can do our clever scheduling mechanisms like shortest job time first and things like that. Okay? So, and then they have a plot of, that's what the plot looks like as we have different bursts. These are the actual bursts, the T, right, versus the guesses, the tau. Okay? Because we're going to get actual times there. right? Because if I'm running a job right now, I can see the burst time by saying, you started here, you're done here, just that time span, the time that you were on the CPU, that's your current burst time. And by keeping track of those with two numbers, just the tau and the t, I can keep this kind of running. And notice that our predictor curve, not exactly, right? This time, in this time period, we're kind of off, right? We're not as, we need some time to respond to this change in burst level, right? But still pretty good, considering we're only tracking a few numbers. Questions on that? Okay, so this is a clever way of answering that question of how do we know what the burst time is? Because we can't know, right? Because we've already brought up those issues of, you can't just look at the code, right? The only way you know how long something's going to take to run on a CPU is run it on the CPU. The only reasonable. Or you can trust the programmer. The programmer can tell you, but then programmers just lie because then their programs will run better, right? Okay, so this is a good way to kind of predict without needing some information. So this combined with our scheduling algorithms, we can do clever things with scheduling. So if we have this predictor and the predictor is pretty good, we know that we can, for example, minimize waiting time. How do we know we can minimize waiting time? Well, because we've already said that optimal minimum waiting time is done with shortest job first. Take this, shortest job first, we have a minimized job schedule, minimized waiting time job schedule. Okay, so just real quick, priority scheduling, shortest job first is an example of priority scheduling. The priorities are based on burst time. Okay, the longer your burst time, the lower your priority. So it's an inverse of your burst time. Okay, priority scheduling is a more general solution where you can assign priorities to different jobs. Okay? This can actually solve one of the problems of starvation if we can manipulate the priorities and not have them fixed based on remaining job time. Okay? You can fix starvation by increasing priority the longer that you wait. In other words, P1 had to wait a bunch of time steps in order to finally be the shortest job, right? Well, if you have a priority system that your priority is not just by the length of your job, but I can arbitrarily change your priority. In other words, increase your priority every time step that you didn't get scheduled. What will that mean? You might be a long job whose initial priority is based on very low because you're long burst time, but you'll eventually get to the point where you waited so long that you're even higher priority than a time unit burst job. Right? So that way you can, as it age, you move up in the priority queue, you finally get to run no matter how long your burst time is. Okay? So, but you can do it, but with priority scheduling, you can set whatever priority you want and then schedule according to that. So in other words, how do you use the priority? Well, we saw how to use the priority with shortest job first, right? We use priority to do what? To order you, right? Highest priority was at the head, lowest priority was at the tail. We do the same thing, but now it's not job length that necessarily says what your priority is. So whoever's the highest priority, head of the queue, lowest priority, bottom of the queue. So then you just step through the queue, but the only twist is you might manipulate priorities, and every time you manipulate a priority, you look at your queue again and you go, oh, let me reorder. And then here's the new order, and I'll take the next one. Okay? And then, finally, round robin. Okay? Round robin is everybody's kind of going to get their own little piece of the CPU. Okay? Time slice. Okay? Each job gets a quanta. Okay? In other words, the time quantum is a time slice. And then we just go through all the jobs, giving them time slices. And then, by the time you're done, by the time you go around enough, all the jobs are done. Okay? What metric does this help us with? Probably not. I say probably not because chances are we'll be doing a lot more context switches in this than in the other ones. Does this help us with wait time? It's a trap. What's that? Wait time might not be constant, but well, actually, it'll be fixed for n for how many jobs you have. But is this good for wait time? What do we know about wait time? What's the best way to minimize wait time? Shortest job first. So is this better than that? No, shortest job first was optimal. Optimal means best. Okay, so we can't do better than that. So what is this helping us with? Here's your list. Response time. This is the best for response time. Why? Because no matter how long you are, no matter what your priority is, none of that stuff comes into play. Everybody is going to get a chance to get onto the CPU and do some computation. Okay? So those are, and this round robin is very straightforward. You just go through, divide it up, and walk through. Okay? You have a lot of context switches. And the idea is that you have a lot of context switches, you're adding a lot of overhead, you're probably reducing throughput because you're not doing useful work, you're doing context switch work. You're probably increasing the overall time it takes to complete jobs. You probably are helping with wait time, okay? Because you probably, I mean, you're not as good as shortest job first, but you're doing pretty good, okay? And but you're probably damaging completion time. But you're doing very, very well with response time. And this is good for things like interactive systems. Five slices. Then there's 10 slices. So you just keep walking through the round robin. Depending on where you put them in the circle, a round robin is a circle. So you probably just put them, I don't know, maybe your scheduler puts them wherever the time slice is at, they get the next 5, I don't know. Or they might get the last 5. But you insert them into the ring, and then you keep going around. But at that point, you have 10 time slices. Everybody gets slower. Right? Okay. So the big factor with round robin, when you use time quantum to, like in other words, slices, is the relationship between how long a quantum you use, how long a time quantum you use, and how long a context switch takes. You want a context switch, the overhead of the dispatcher switching from one job to another, right? You want that to be a very, 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 very small compared to the time quantum. In other words, the percentage of time that a dispatch takes, that a context switch takes, compared to the quantum, is how much of your CPU time is wasted, right? If a context switch is 1% as long as a quantum, 1% of your CPU time is wasted. If it's 10%, 10% of your CPU time is wasted, right? Because however long it is how long is in between each quantum. And these are some graphs. Increasing the time quantum doesn't necessarily lead to an increase in the turnaround time. Okay? Because it's not a nice little curve because it depends on the time that the processes take and how much you break them up by these quantum. In other words, if you stop something right before it's about to be completed, you probably would have been better off just completing it rather than switching. Okay? But we're gonna stop there. And Thursday we'll talk about multi-level queues, like different queuing systems to kind of combine some of these ways. And then some examples from real operating systems, like Windows and Unix and Linux. Okay. So, but those are the basics of the algorithms. Take a look at them. In your book, there's some really good walkthroughs of just, here's the jobs you get, here's why you get this number for the average wait time, and here's why it reordered this way. Take a look at those because, like I said, those are some good ideas for things like projects. If you want to tweak one of the algorithms or something like that and see what happens, or you just want to display some of them side by side and see how different mixes of jobs back to them. Those are good ideas for projects because they're very it's very straightforward to write a step-by-step simulation. Okay.
That formula, calculating the predicted
Right. Burst.
burst time, does that come from Bayesian statistics?
Yeah, isn't that like previous prior history determines future behavior?
I don't know much about it, but it sounds like that's what it is.
I think the concept is the same. I know that I don't know how Bayesian samplers and stuff like that how they typically do things,
Yeah.
but I don't know if it's the exact same theorem, but it's the same idea. It's
Sure.
the idea of just looking at the behavior, the past behavior.